Till now, we studied that when a current is passed through a conductor, it generates magnetic field around it. The reverse of this, that is, the production of electricity with the help of magnetism, is known as electromagnetic induction. So, let's begin with our next topic, that is electromagnetic induction. The idea of electromagnetic induction came in Faraday's mind in 1831. This brought a revolutionary change in the field of generation of electricity. So let us understand how electricity is generated with the help of magnet. So what we can do, we can take two magnets with north and south pole on it. So I keep the opposite faces facing each other. I took one conductor, this is my conductor, and I placed it across one magnet, and it is in between the magnetic field. So this is in between the magnetic field, and this is perpendicular to the magnetic field, and I connected a galvanometer. So galvanometer is nothing but a device which helps us to know whether there is flow of current or not. So it is used to detect the presence of current. In galvanometer, the needle is always on the zero. Like other device, we have zero on leftmost end, but in galvanometer, zero is in the center, and on right hand side and on left hand side we have numbers. So when there is current in the circuit, it gets deflected. Galvanometer is always connected in series to know the presence of current. So if there is some presence of current, when we move the conductor, we can detect it with the help of the galvanometer. So as soon as you lift the wire upside, the galvanometer deflects. When you bring it down, it again deflects to the other end. If you move the wire up and you wait over there, then galvanometer will come and it will stop on zero. If you move it down, it will again deflect in the opposite end. This shows that when a conductor is moving in the magnetic field, electric current is generated. This type of current which is generated is known as induced current. So this can be seen with the help of one simple experiment. In this setup, my conductor was moving. So I will take one more experiment in which I will move the magnetic field and my conductor will be fixed. So for that, we will take a coil and we will attach it with a galvanometer. So this coil is attached to a galvanometer. Now I will bring one magnet close to it. As I bring the magnet close to the wire, the galvanometer starts showing deflection. If I stop in between, the galvanometer will come back to zero. When my magnet is moving up, its deflection are in one direction. When I pull my magnet out, its deflection are in opposite direction. Let us see with some small piece of a copper coil how this is done. Now this is a copper coil which is wounded. If I move my magnet inside like this, then there is deflection on the galvanometer. If I move it outside, then there is again deflection, but it is in opposite direction. This experiment also helps us to understand that when there is change in the magnetic field in a conductor, there is presence of, or we can detect the presence of electric current. So with the help of these two experiments, we can say that when there is change in the magnetic field, current is induced. This current changes alternately, so we call this generated current as alternating current, which we represent as AC. Because when our magnet is going inside, when we are pushing it, our current is generated in one direction. When we are pulling it out, it is in other direction. So like this it is in one direction, then it is in another direction. Again one direction. So it forms a wave kind of structure. So this is nothing but your alternating current. So now we know what is induced current. But in which direction it is induced, to know that we should know Fleming's right hand rule. So in Fleming's right hand rule, your thumb will point the movement of the conductor and it is perpendicular to the magnetic field. Your magnetic field is indicated by your index finger and your middle finger will give you the direction of induced current. So these three are again perpendicular to each other. So you have to point your thumb in the direction of the motion of the conductor and your index finger should be in the direction of the magnetic field. So let us take our previous example where we took two bar magnets and we placed a conductor in between them. So these are our two bar magnets and our conductor was placed in between this, right? And here we took one galvanometer to know whether current is generated or not, right? Now, if you see, my magnetic field is in this direction from north to south, and I moved this coil up and down. So now my magnetic field is in this direction and I am moving my coil up. Now when I am moving my coil up, my middle finger is going backside. So my induced current is in this direction when I am moving my coil up. If I move my coil down and my magnetic field is in this direction, right? If I'm moving my coil down and my magnetic field is in this direction, then my middle finger is coming this side. If I'm moving it down, then my induced current is in this direction. So with the help of Fleming's right hand rule, we can know the direction of induced current. Now let us see electromagnetic induction by using two coils. So here you can see coil A and coil B. If you notice it clearly, coil A is attached to a battery and a key, whereas in coil B we have only a galvanometer, right? Now what we are going to see, we are going to see electromagnetic induction using two coils. That is, when the current flows in coil A, does it have any effect or does it produce current in coil B? So when I switch it on, when I switch my coil A on, current starts flowing through coil A, and as soon as I switch it on, there is some deflection in the galvanometer. And again it comes back to its normal position. So that deflection is only for a second when I switch it on. After that it comes back to 0. When I switch it off, the galvanometer deflects on the other side and again comes back to 0. This shows that induced electric current is also produced when we take two coils. But why this current was only for a fraction of seconds? When I switched this on, my coil A on, current started flowing from the coil, which turned this into a magnet. So the coil B came in the influence of the magnetic field which was produced by coil A. And because of that, we came to know that there was some current. But why that current was not there for a long period? Because the magnetic field was steady when the current started flowing from it. It was similar when we push in a magnet into a coil. In the same way, when I switched it off, it showed me some deflection and it again came back to normal. This action was similar to the pulling out of a magnet from a coil. So that was the reason why there was induced electric field in coil B only for fraction of seconds. Because when my current was flowing for a long time, my coil was in steady magnetic field around it. It was not in the motion. That's why there was no current in it. If I keep the switch on off, if I do the switch on off continuously, then here also the current will continuously deflect from one end to another end. And in the same way I will get AC current here also, that is alternating current here also. So this induced current helped us in a major way, that is we got electric generator with cause of this invention. The same principle is applied in electric generator. So we will just have a look at electric generator so that it will be clear for you how the electricity is generated with the help of magnetic field. So this is a rough diagram how your electric generator looks. Here we have two magnets, two strong magnets, and the magnetic field is from north to south. It is uniform magnetic field, right? In this uniform magnetic field, we kept one armature. Armature is a rectangular structure of a conductor. This armature is connected to two slip rings. So it is connected to two separate slip rings, and those slip rings are connected to a galvanometer. Okay? So G for galvanometer and G for generator. So in generator we use galvanometer. It is easy to remember then. In motor we have a battery over here and we have one ring. Okay? Now what happens? Here is one axle which is passed from here. Okay? So if you rotate the axle, the armature is going to turn. If your armature is in motion and if it is in a magnetic field, it generates electricity. Right? We know this fact now. So because of this rotation in the armature, electricity is generated. And so this is known as electric generator. If you want to know in which direction the electricity is generated, you just need to know your right hand rule. So if I say my armature is moving upwards, if it is moving upwards, then my magnetic field is in this direction and my motion is upwards. So with the right hand rule, I can know that my current is flowing this way. If I move my coil downwards, then my magnetic field is in this way and my magnetic field is in this way and my motion is down, so my current is going to get generated. I'll mark that as my current is going to get generated in this way. If it is moving down, then it is going to get generated in this way. Okay? So from this, we can know that when there is a change in position of armature in a strong magnetic field, current is generated. This current which is generated is AC current, that is alternating current. If you want direct current, then instead of these two split rings, we can use a single ring as we used in motor. If we use a single ring, then we get direct current, in which there is no change in the direction of current. So in this way, a revolutionary change occurred when Faraday thought that if there is an effect of electric current on magnetic field when it moves, then electricity can be also generated when there is motion of a conductor in the magnetic field. And this brought a great help to us. So this was all about electric generator and induced current